Welcome, ladies and gentlemen. So what I'd like to do is show you how to solve trigonometric equations by using your trigonometric or your Pythagorean identities. So if you do not have your identities, I'd make sure you have them in front of you so you can make sure you verify and kind of work your way out with this. And also having the unit circle is going to be helpful. Now, I have 4 problems up here, and it's pretty algebra intensive. I'm going to be doing a lot of algebra work, a lot of factoring, and so forth. And I'm also going to kind of move quickly through the Pythagorean identities and the unit circle. So I don't want to lose you, but I also don't want to make a video that's going to be 40 minutes long. So I'm going to at least talk through everything, but I'm not going to be able to as far as showing all of my work. But if you've watched my previous videos, hopefully you're kind of caught kind of back up the way that each of these problems work. We're only just having a little bit extra changes and differences here because now we're having, not only are we having more than one trigonometric function, sine, cosine, secant, tangent, but now we're also dealing with problems that are going to also need to be factored. So the reason why, again, we want to use factoring is because I can't isolate. Remember, the idea of solving is to isolate your variable. Well, I can't isolate my variable in cosine and my variable in sine at the same time. The only way I can do that is to set it up as a product of two factors or expressions equal to 0. So therefore, I can use the zero product property to set both of those expressions equal to 0, and then I can use my inverse operations to solve. So first thing we have here, though, is I have an expression, and to get it to zero product property, you got to think of like factoring. Well, think of like cosine and sine as different variables. That marker doesn't even work. Think of this as like 2x squared plus y minus 1 equals 0. If I was going to say solve, you'd be like, well, those are two. You can't, you have an x and a y. Which one do you solve for? You can't just factor it like you've done before for like quadratics. So the only way we can do this is to get them to be the same. And that's true with factoring when you're dealing with trigonometric functions. So what I'm going to do is I see that I have a cosine squared. So that automatically triggers in my brain, use the Pythagorean's identities. So I can rewrite cosine squared as sine squared, right? I can by using my Pythagorean identities. So you're going to want to use cosine so I can rewrite my whole expression in terms of sine. So by using my Pythagorean identity here, I have 1 minus sine squared of x plus sine of x minus 1 equals 0. Now you see I can distribute my 2 here, and I get 2 minus 2 sine squared of x plus sine of x minus 1 equals 0. Okay? Now I'm going to rearrange this. Okay? So I have the largest power here first. So I rearrange this as a negative 2 sine square of x plus sine of x. 2 minus 1 is going to be a positive 1 equals 0. Now, I don't like factoring when my first term is negative. So what I'm going to do is I'm going to divide both sides by a negative 1. And as long as you're doing the same operation to both sides, you're not changing the problem. So by doing that, I now obtain 2 sine squared of x plus, minus sine of x minus 1 equals 0. Now that, for me, that's much easier for me to be able to factor. So now I have a quadratic trigonometric expression, all in terms of sine. Now I can go and factor it. So if you watch my video for the factoring one, you could always replace the signs of x for x's and just factor it that way. But what I see is if my 2 first terms have to multiply to give me 2 sine of x, I am going to then write one as 2 sine of x and the other one as sine of x. I need 2 terms that are going to multiply to give me negative 1, so that'd be positive 1 and negative 1. However, the middle term has to add to give me negative sine of x. That means the larger product is going to be negative. So I'm going to multiply 2 sine of x times negative 1 and sine of x times positive 1. Because when you double check your work, these two multiply to give us 2 sine squared. These two give us negative 1. And then my middle terms, sine of x times 1 plus 2 sine of x times negative 1 adds up to give me a negative sine of x. Okay, so you can always check your work by going back and checking FOIL. Now I have an expression times another expression equals 0. So I can apply the zero product property. So I do 2 sine of x plus 1 equals 0, or sine of x minus 1 equals 0. Then I just go ahead and solve using my inverse operations. And you can see I'm getting very, very low here on my work. So I have sine of x equals 1/2, or add 1, or sine of x equals +1. So to determine my solutions here, I'm going to have to go back to the unit circle and determine, all right, for what angle does sine of x equal 1/2? To solve this technically, you would take the inverse sine of both sides, and then you'd have x equals sine inverse of 1/2 and x equals sine inverse of 1. I just ran out of space, so I'm just going to say it out loud of what we're asking for. The sine of x equals 1/2. If we're trying to solve for x, we're trying to say the sine of what angle equals 1/2. So we go to our unit circle and we say, all right, well, the sine of what angle? Remember, the sine of an angle represents the y-coordinate. So when is the y-coordinate 1/2? Okay? And for those angles, you can look at that. And that's the first angle I notice here is this angle, which is pi over 6. Because that angle is square root of 3 over 2, comma, 1/2. The y-coordinate is 1/2. So I can say one solution is x equals pi over 6. But remember, sine is positive in the first and the second quadrant. That means this angle is also going to work. Well, what is that angle? That angle is 5 pi over 6, because that gives you, if you look at your unit circle, negative square root of 3 over 2, comma, positive 1/2. So another solution is 5 pi over 6. Then we need to determine, well, when the sine of x is equal to 1. For what values does x equal 1? Well, we have this coordinate point up here, 0, comma 1, where the y-coordinate is equal to 1. That angle is pi halves. So you could also say pi halves is your last solution. Now, please remember that I have a constraint which I didn't talk about yet. You can see my constraint here is between 0 and 2 pi. That's why I only have these 3 solutions, because those are the only solutions where my sign is positive, is in the first and second quadrant. That's the only solutions that are around between 0 and 2 pi. So now let's go ahead and get into the next one. So you can see this is kind of this very similar of a problem. 2 secant squared of x plus tangent squared of x minus 3. But now they're both squared. So which Pythagorean identity do you want to do? Do you want to rewrite secant as tangent squared, secant squared as tangent squared, or do you want to rewrite tangent squared as secant squared? Well, you could do either or. Doesn't really matter. I always like to use the trigonometric functions I'm most familiar with, which is sine, cosine, and tangent. It's much easier to do that than solving for the reciprocal function. However, you can do both. Well, if I was going to rewrite then secant as tangent, that's simply going to be 2 times 1 plus tangent squared of x plus tangent squared of x minus 3 equals 0. Then I apply to my distributive property, and I'm left with 2 plus 2 tangent squared of x plus tangent squared of x minus 3 equals 0. Now in this case, you have a tangent squared and a tangent squared, so I can combine them. Over here, I had a sine squared and a sine. I couldn't combine them. That's why I had to factor. This one, we don't have to factor, at least not yet. I just need to combine them. So 2 tangent squared plus tangent squared is 3 tangent squared of x. 2 minus 3 is going to be negative 1 equals 0. Now, I don't have to factor. I can just use the inverse operations now to solve. So I'll add 1 to both sides, and I get 3 tangent squared of x equals 1. Divide by 3, divide by 3. And I get tangent squared of x equals 1/3. Again, to solve for tangent, take the square root of both sides, and I get tangent of x equals 1 over the square root of 3. You can break up the square root of 1/3 as the square root of 1 divided by the square root of 3. The square root of 1 is 1. But now I need to rationalize the denominator. So therefore, you can say that it's equal to 1 over the square root of 3, or it's also equal to the square root of 3 over 3. Because square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. OK, so now I need to go in and say, all right, for what angles tangent of x, the tangent of what angle, x represents our angle on our solution, is equal to the square root of 3 over 3. Now remember, when we're finding the sine, like we did over there, sine represented the y-coordinate. So we just looked at our angles on our unit circle and determined which points when our y-coordinate was 1/2. Cosine, it'd be the x-coordinate. Remember, tangent is y over x. So I got to look at this and say, all right, for what angles, when I do y over x, do I get square root of 3 over 3? Well, fortunately for this problem, we actually have that angle already up there. Because if you do y over x for the angle pi over 6, what you get is same angle. So therefore, I know one of my solutions is going to be square pi over 6. So I can say x equals pi over 6. However, we are going to differ, though, from sine and tangent, because sine is positive in the first and the second quadrant. Tangent is positive in the first and the third quadrant. So I got to look for that similar angle that's in the third quadrant. And that similar angle has the points here, negative square root of 3 over 2, comma negative 1/2. When you have a negative over negative, that's positive. That's why tangent is positive in the third quadrant. So we just need to determine, well, then what is that angle? Well, if this would be pi, which is 6 pi over 6, this would be 7 pi over 6. Okay? And you can see that those two angles, those are going to be our only two angles between 0 and 2 pi. All right, so now these were nice because we set them, they're already set equal to 0. So we knew we could just rewrite them in terms of sines and cosines and then apply factoring. Here, I don't have this set equal to 0, right? So the main important thing we need to do then is get them on the same side. So what I'm going to do is I'm going to subtract cosine of x. So therefore, I'm left with 3 sine squared of x minus cosine squared of x equals 0. Now I had it set equal to 0. I know, OK, I can now I can use my factoring techniques, right? Because we have a sine and we have a cosine. So we're probably going to have to either use factoring or combine them. Well, the first thing we want to do before determining if you have to factor, because I don't know yet, you either have to factor or they'll combine. We've got to get them to be the same trigonometric function. And we could either do that for cosine or we could do that for sine. I think doesn't really matter which one, really. Since I already did one for sine, I'll do this one for cosine. But really, it can be a flip of the coin. So I'm going to rewrite sine squared in terms of cosine squareds. So therefore, I'll solve the problem in terms of cosine. So in doing that, I'm going to do 3 times cosine is going to be, or sine squared written in cosine is going to be 1 minus cosine squared of x. And that's going to be minus cosine squared of x equals 0. OK? So now I go ahead and apply my distributive property. And what I obtain is 3 minus 3 cosine squared of x minus cosine squared of x equals 0. Well, now these are both cosine squared of x, so I can combine them. So I'll be left with 3 minus 4 cosine squared of x equals 0. Now, I don't have to factor. Since I was able to combine them, they're like terms. These are not like terms. These are. So I can combine them. And now I just use my inverse operations to solve. So I'll subtract a 3 on both sides. I'm left with negative 4 cosine squared of x equals negative 3. Divide by negative 4. Divide by negative 4. So I have cosine squared of x equals positive 3 over 4. To undo the square root, take the square root of both sides. Ooh. Mr. McLogan, I found out my problem. Good catch. I just realized it. I'm going to go back to that problem in just a second. So therefore, I have cosine of x is equal to the square root of 3 over 4. But remember, when you take the square root, and I'm sorry, I was working a little bit too fast. When you take the square root, you have to make sure you introduce plus or minus. So therefore, this ends up equaling the square root of 3 over 2 plus or minus. Over here, this is also going to be plus or minus. So not only am I going to solve when that is positive, I also have to find the angles when that is going to be negative. So that's going to be the angle in the second quadrant and fourth quadrant. So fortunately, going back to this problem real quick, tangent is going to be negative here. Same angle, y over x, that still produces it, but that's negative. That's the angle 5 pi over 6. And then in the fourth quadrant is going to be 11 pi over 6. Sorry about that if I confused you originally. Just to make sure, whenever you introduce taking the square root, you got to do plus or minus. So I took the square root of the top and the bottom. The square root of 3 is just going to remain the square root of 3. And the square root of 4 is just remain 2. So I go back looking at my unit circle, and I say, all right, so when is the cosine? Actually, I already got this. That's not too bad. When is the cosine going to equal to positive square root of 3 over 2? Well, you can see here, I already have this angle, pi over 6. The x, or sorry, cosine of x So cosine of what angle equals positive square root of 3 or negative square root of 3? Well, it's positive here, and it's negative here. It's negative here, and it's positive over there. So these are going to have exactly the same solutions. So x is going to equal pi over 6, 7 pi over 6, 5 pi over 6, and 11 pi over 6. Okay, because here, for the angle pi over 6, cosine is positive square root of 3 over 2. Over here, 5 pi over 6, cosine is negative square root of 3 over 2. Here, it's negative. Here, it's positive. So that works for all of them. All right, in the last example, this is a good one. I like this one because this one confuses a lot of students because you say, oh, well, Mr. McGowan, there's no trigonometric identities. Well, sometimes we have to get a little creative. And we're going to need to create trigonometric identities. So to do that, what I'm simply going to do is I'm going to square both sides. Squaring is an operation, right? Just like dividing by -1 on both sides, you can square on both sides. Just remember, when you square the left side, that's sine of x plus cosine of x times sine of x plus cosine of x. Okay, please make sure you multiply them. Then you're going to have to use FOIL, and that equals 1. Okay, so just make sure you do your FOIL. I'm not going to write this out. Hopefully you know your FOIL by now, but I will write in the answer because this is it produces a perfect square trinomial, which is going to give you sine squared of x plus 2 sine of x cosine of x plus cosine squared of x equals 1. Whew. OK, well, now we have sine of x plus cosine of x. We know that goes to 1, so I'm left with 2 sine of x cosine of x plus 1 equals 1. Again, if we need to go ahead and use factoring or so forth, I can just get rid of this. So I can subtract a 1 on both sides. That's going to leave me with a 2 sine of x cosine of x equals 0. Then I can use the zero product property, but I can also get rid of this 2. I don't really need the 2. So I'm going to divide by 2 on both sides, which is going to leave me with a sine of x cosine of x equals 0. Well, now I have it as a product. See, here it was added, so you can't separate them. But when they're separated by multiplication, you can separate using the zero product property. Sine of x equals 0, and cosine of x equals 0. So now we go back to our unit circle, and we say, all right, when is 1 comma 0, 0 comma 1, -1 comma 0, and 0 comma -1? For what angle is y equal to 0? Right? That's basically what we're asking. What angle, the sine of what angle is equal to 0? Well, you can see that sine represents the y-coordinate, so we have two angles. We have the angle 0, and we have the angle pi. So we could say x equals 0, and x equals pi. Actually, let's just write it out like that. Then for cosine of x is basically asking for what angles is the x value 0. Well, that's going to be pi halves and 3 pi halves. OK. The one problem, though, that we need to go back and make sure we check our work here is when we are squaring both sides here, we got to look for extraneous solutions. So it's very, very important. It's important for all of these to double check your work, make sure you did it correctly. But especially when you're squaring both sides, you got to make sure you check for extraneous solutions. So basically what I'm going to do is I'm going to plug my angles back into my original equation and determine if they work or not. And I'm going to kind of go a little bit quickly with this, so you're going to want to make sure you follow along. So if I plug in 0, angle 0, the sine of 0 here is 0. The cosine of 0 is 1. And that equals 1. That's verified. So that works. Pi. The sine of pi is over here. The sine of pi is -1. I'm sorry. The sine of pi is 0. The cosine of pi, though, is -1. That does not work. Okay? Then let's go to pi halves. The sine of pi halves is 1. The cosine of pi halves is 0. 0 plus 1 is equal to 1. So that one's verified. Then let's go to 3 halves, 3 pi over 2. The sine of 3 pi over 2 is -1. Plus the sine of 3 pi over 2, or sorry, the cosine is 0. That does not equal -1. So therefore, we actually have two extraneous solutions, pi and 3 pi over 2. Therefore, our only two solutions are going to be 0 and pi halves. So there you go, ladies and gentlemen. That is how you solve trigonometric equations using your Pythagorean identities. Thanks. Ah! Yes.